All right, let's get started. Reminder, there's a quiz on Monday. There will be 3 questions, 2 true-false without any justification. The third question would be a true-false with justification in 2 parts. The first part is just justification. The second one is the usual true-false with justification. Are any questions on the quiz format? Again, as a reminder, for an incentive for you guys to fill in the official course evaluations, if at least 85% of you fill in the course evaluation, then I'll release 1 question. If at least 95% do, I'll release 2 questions. And as of yesterday, the percentage was 24. And I believe this is open till, I believe, December 10th. And so you will still have enough time to know the question if at least 85% of you fill in the forms. Demos for CSS week, I believe we have gotten quite a few in the last few days. That's great, but if you're still on the fence, there is a competition tomorrow, so please consider that. Also consider volunteering for the CSS week if you don't want to do a demo. It's a lot of fun, and you should participate. Any questions on logistics? All right, so we wrapped up the problem of, one way to think about the problem is trying to schedule as many idle cycles as possible. So you have n jobs where the ith job takes wi cycles, or you can think of them as numbers w1 to wn. And you have a total number of cycles that you have, or you consider this as a budget that's capital W. And the question is, how many of these can you schedule so that the total number of cycles or numbers that you use up is no more than your budget capital W, but you get as close to W as possible. So the point is, you want to schedule as many jobs as is possible and be as close to capital B, your budget, as possible. So we use dynamic programming to solve this problem. And again, as a reminder, here are the kind of 3 rules of thumb that you generally should keep in mind while designing dynamic programming algorithms. The first is you want polynomially many subproblems. So in this case, the subproblems are for all values of j from 0 to n. So when you look at a subproblem with j, you're looking at the first j numbers, and you have a budget that goes between 0 and w. Okay. So the number of subproblems is essentially of the order of n times capital W. And actually, I'll come to it shortly. It's depending on how large capital W is, this need or need not be polynomial many. Then you want an optimal solution that can be computed from solutions to subproblems. And this basically needs forms a recurrence formula. In this case, it's quite long, so I'm just not writing it down. But we did it last time. And there is an ordering among subproblems. So for this subset sum problem, the observation was, if even though you don't see it here, if you look at the recurrence, opt of j comma b actually only depends on these values in the previous column. So the algorithm essentially then is you have this n plus 1 times w plus 1 matrix. The first 0th column is all zeros, and then just keep on filling the columns one by one till you fill in the last column, and then you output the top right entry, which is opt of n comma capital W, which is what you're interested in. Again, this only gives you the maximum value that you can get out of the maximum weight. And if you actually have to compute the actual subset of numbers or subset of jobs that you pick, then there's a simple recursive way to do it. So you start off from the opt n comma W value, and that's computed. If it's computed by a max, then you know whether n is in the solution or not. And depending on that, you kind of go back. All right, so as we saw last time, essentially what you're doing is you're filling a matrix with order and W entries, and you're only spending constant amount of work to fill this matrix in. And And that's also basically the amount of space, and that space is needed if you actually need to compute the actual subset. Otherwise, you can do better. So one question that I talked about briefly, and I want to again stress again, because there always seems to confusion about what is the actual input size. So in this case, let's say you have n jobs, and the ith job takes w cycles, right? And so each of these wi, so there are n numbers, and then you have this another single value capital W, right? But the point is the number of bits needed to represent the budget is not W, it's log of W, right? So your input size is something like n plus log W, right? Not n plus W. So in that sense, if W can be large and capital W, the budget can be, say, if it's exponential in n, then this algorithm is not polynomial runtime, even though the input size is n plus log of 2 to the n, which is n. Okay? So it really depends how large W can be. If we can assume that capital W, the budget is polynomial in n, then you're fine. This is polynomial time. But in general, if it's not specified, then it's not polynomial runtime. It's what's known as pseudo-polynomial. So it's polynomial in part of the input, but not the rest. Okay? Are there any questions on the subset sum problem, or the dynamic programming that we saw, this runtime? Alex.
What is meant by log W bits needed? Why is that?
Because it's a number from 0 to W, right? So to represent that number W, you only need log W bits. So as a similar example that was in one of the solved examples of one of the earlier homeworks, if I give you a number n and ask you whether that's prime, right, the input size for that is not n but log n. Right? And so when you say you want an algorithm that runs in polynomial time and tells you whether n is a prime or not, it needs to run in time that is polynomial in log n. And that problem was actually open till 2000. It's been solved only kind of recently. Any other questions? All right, so we are actually down to our last problem for the semester. We're going to come back to the shortest path problem. Right? So we've already kind of looked at two versions of this. When we were doing BFS, we observed that if you have an unweighted graph, then BFS actually computes the shortest distance from a given source to all the other nodes. We also looked at the weighted version. So now you're given a directed graph, but now the edges can have weights, but these weights are non-negative, so they're greater than or equal to 0. In that case, we saw Dijkstra's algorithm solves that problem. But now we want to look at an even more general case. So now we want to allow these costs to be negative. And so one question that comes is like, why would negative make sense? Like positive makes sense if it's actually a distance you want to go from point A to point B, then positive value obviously makes difference, but when can say a negative cost make sense? And this is when the CE is actually a cost. So let's say to go from point A to point B, you have to do some transaction, right? And you have to pay that much amount of money, right? And so if the cost is 10, you say pay $10. But if it's minus 10, then someone pays you $10. Right? And so in that sense, when you have like this notions of cost or money, and there can be transactions going on both ways, then even negative makes sense. Okay. All right, so in this case, the input is directed graph. You have edge costs, and the edge costs can now be negative. And now we have a terminal vertex T, and you want to compute the shortest path from every vertex X to this terminal vertex T. Note that this is slightly different from how we did BFS and Dijkstra, where we told you where to start with. So S was fixed, and you want the shortest path to everything else. Here we're starting off with the terminal T, and you want all the shortest path to this terminal. Okay? The main reason I did it was because that's how it's done in the book. And the reason why it's done this way in the book is there's a following section that utilizes this. And this is the for some routing problem, and this is the correct version to look at. Okay, but once we look at do the algorithm, you can go back and think about it. Changing it to the case where you're given a start vertex is pretty much the same. Okay, so there's no inherent difference between whether you're given one start and you want to go to all the nodes, or you're given one sink and you want to go to that destination. All right, so this is what you want to do, but yeah.
Is this like a similar problem to like value iteration?
What do you mean by value iteration?
So you have it's like a dynamic programming problem where you have like actions you can take, and each action gives you like a reward or like a minus reward. You kind of have to you have to calculate the optimal series of actions.
Right. So just to repeat Evan's problem more generally, you can think of them as every node is a state that you're in, and depending on actions that you take, you can go out and either you pay money or you get money. And you can say things like, I want to go from the start configuration to this end configuration, and I want to spend as little money as possible. Yeah, this would correspond exactly to this problem. Okay, except here we want not just one destination, but all possible. But yeah. Any other questions? Okay, so I claim the problem is not quite well defined if I just stop here. Do you guys see any issues with this definition of the problem? Evan?
I'm not sure it's bad.
Okay, it's kind of getting there, but why are you asking that?
Like the least cost path or like the fewest nodes that you have to distribute?
Right, okay, so the shortest path in this is least cost. So given a path, you add up all the edge costs, and the one with the minimum cost gives you. But there's more than, I have to ask your name. Wade. Sorry?
Is it possible for the shortest path to be
Okay. Right.
What if you can take infinite cycles, wrap up?
Right. So the issue is not that this problem is not well defined, it is well defined, but what if you have a negative cycle? Right? So you have this, you go from here, you pay 100 minus 1,899, you make one round, you get -1, right? And then if you want to do the smallest, you just keep on doing it forever and ever, right? So the smallest is minus infinity. The issue with that is you cannot represent an infinitely long path, right? So what we're going to assume is the graph has no negative cycle. So the graph is allowed to have negative weight, negative cost. It is allowed to have cycles, but it cannot have both in the sense that it cannot have a cycle where if we add up the edge cost of that cycle, the total cost is strictly smaller than 0. Okay. Any other questions? All right, so what we're going to do is look at the dynamic programming to solve this problem. I'm actually trying something new. We are going to make 5 attempts to solve this problem. We'll finally succeed, but we'll kind of go through things and try to see why they don't work. And actually, the algorithm that we're going to finally converge to is Bellman-Ford, and it's like one of the very first dynamic programming algorithms that were ever designed. Okay. All right, so we are looking at the shortest path problem. And so the input is directed graph G. And for all edges in E, you're given cost C. And I said it's not necessary, like in the case of Dijkstra, that these be non-negative. They can indeed be negative. but you're not allowed any negative cycles. You're also given a terminal vertex T, and you want to output for all S in V shortest ST path, and here by shortest the cost of a path and so the cost of a path is the sum of costs of the edges in the path, and when I say shortest, it means you want to find the one with the minimum cost. So for among all ST paths, find one that has the minimum cost. So as I had mentioned, I'll do it again. So unlike the case of the Dijkstra algorithm or the problem we looked at, here we have one destination. And whereas in Dijkstra we had one source. Okay. All right. So given that we know Dijkstra, what should be the first attempt to try to solve this problem? Mark?
Can you run Dijkstra from the T node?
Right, so the point is, why don't we just run Dijkstra? And let's even consider the simplest case where I give you S and T. And so then you can start Dijkstra from S and then see what cost you get from T. Okay. So let's even assume actually let's not do that. So attempt 1 is just run let's run it for each source. Okay, and of course, if this works, I have to run it for n times, but if I only care about polynomial time, this doesn't matter. But this fails miserably, right? So not only does it fail for the case it doesn't even need cycles in the directed graph. So I'm going to come up with an example which is a DAG. It will have just one negative edge weight, and even that's enough to just fault the algorithm. Okay. So this fails miserably. So here's one example. And I believe this might be the smallest example that you can come up with. So there are 3 nodes. The direct edge from S to T has cost 1, S to U has cost 2, and U to T has cost -3. Okay. And so let's say, so now I start Dijkstra at S. What will Dijkstra do? It will look at all the neighbors of S, pick the one that has the shortest outgoing edge, and say that the shortest path from S to that chosen vertex is that shortest edge, right? Which in this case is T. But the issue is the shortest path is the longer one where you have to go via U. Okay. So in this case, initially, if you remember, there was a d prime value which you calculate as the best possible path from the current set of nodes to every node that's outside or the nodes that you have not considered. So d prime t is 1, and d of u is 2, and so that implies in this case Dijkstra sets d of t to be 1 and basically says ST is shortest path, but this is wrong because the shortest ST path is SUT. Okay. Now, if you remember the proof of Dijkstra's algorithm, you'll see this is exactly the bad case that the proof doesn't handle. Right? So the reason why this argument works fine for the case where there are no negative edge weights is, you know, if you pick the edge with the shortest cost going out from S, even if you have a longer way of getting back to that other endpoint, since all the edges outside will have cost greater than or equal to 0, you cannot do anything better. And here is basically the exact example to show why that argument is the best possible for Dijkstra. Okay. Are there any questions? Is everyone okay with this? Okay, so again, the reason why this doesn't work is because Dijkstra needs all the edge costs to be positive or non-negative, and that's not the case here. Right? So if you can't do that, then maybe one way to think about this is maybe let's still try to use Dijkstra, but maybe use a reduction. Maybe we can change the edge costs in such a way so that all the edge costs are positive, and then we can run Dijkstra. So what would be one way to make sure all the edge costs are greater than or equal to 0? Right, so the point is, the issue is you might have an edge weight that's negative. Just take that absolute value of that thing and just add it to everything else. Okay. All right, so let's try that. So the idea is try a smarter reduction to Dijkstra. And so in particular, it doesn't even have to be the absolute value of the largest negative edge weight. I mean, as long as you pick some value that's strictly bigger than that, that's fine. So you add a large enough number to all edges so that all the new edge costs, if I denote them by say C prime, is greater than or equal to 0. And then the idea is just run Dijkstra on new instance. Do any of you see an issue with this? Alex?
It doesn't work.
Yes, but why?
Well, I just tried it. So that's a counterexample. I don't know.
Okay, so Mehmet?
I was just going to say that it would give you a different path. So it would give you a path, but it would give you a different path than compared to what you want.
All right, so it turns out the issue with adding the same cost to all the edges, by the way, this I believe was a true-false question on Piazza 2, is this will disproportionately ignore paths that have lots of edges in them because you're adding large numbers to all of them. Right? Whereas it could be the case that really what you needed where the shortest path is actually one with lots of edges. So in particular, I mean, all of this is combined, as Alex says, there exists a counterexample. So here's one. So I don't think this is the smallest possible counterexample, but that's okay. So let's say this is my original graph. The costs are 1, 2, 2, and minus 4. Okay. So in this case, the shortest ST path is this long guy, is SUWT. And let's say we add 4 to all edges So as Evan said, you can just add the absolute value of the smallest edge. So again, the edge structure remains the same. It's just the edge values that are changing. So the top guy becomes 5. This becomes 6, 0, 6. And now in this case, the shortest path in the new graph is just the direct edge from S to T. So the shortest ST path in this case is just the edge from S to T. And this is not good, right? Because what we really wanted was this SUWT as our answer, because that's the shortest path in our original instance, which is what we're interested in. And adding this large enough positive value to all the edges basically changes the actual shortest path between them. Okay? So this won't work either. Is this clear? Are there any questions on why these two attempts of using Dijkstra do not work? Okay, so it turns out there's actually no known greedy algorithm for this problem. And so we're going to try to come up with a dynamic programming algorithm to do this. So in particular, we're going to build towards the Bellman-Ford algorithm. And as I had mentioned, this is one of the first dynamic programming algorithms. And before we go there, we're going to argue a statement that I think I had mentioned way at the beginning of the semester, but now is a good time to recall it because it's going to be useful in the final algorithm. And it says something really simple, which is if you look at the shortest path between any two nodes S and T, there will always exist a shortest path that is simple, i.e. one that doesn't have any cycle. And the argument is, well, if we had a shortest path that had a cycle in it, right, remember we have no negative cost cycle. Right? So you can just throw that cycle away, and you're guaranteed that the cost cannot go up. And so you've removed one cycle. And you keep on doing this till you've just thrown away all the possible cycles. So even if someone gives you a shortest path that has cycles in it, you can just keep on throwing the cycles off one by one, and ultimately you're going to end up with a path that does not have any cycle in it. Okay? So we're going to write that down, go through that argument again, just to make sure everyone's on the same page. So if G has no negative cycle, then that implies for all vertices S and T, there exists a simple ST path. And as I said, the proof idea is basically a simple proof by contradiction. Assume there exists one, and then we argue we can just throw away cycles. Okay. So for contradiction, assume all paths, shortest ST paths have a cycle in them. So let's say I have a path P, you start from S, and somewhere in the middle you have a cycle, and then you continue on your merry way till you reach T. Okay. So the idea is just remove the cycle. So more precisely, if there exists a cycle T, let P prime be the path that you get from by throwing away all the edges that are in the cycle. So in this case, what I'm going to do is I'm going to just throw away all of this. So the first thing to note is that the cost of P prime is cost of P minus the cost of the cycle that you threw out, and we are assuming the cost of all the cycle is greater than or equal to 0. Okay. So this is cost of P as no negative cycle exists. And so you repeat, if necessary, to get a simple path with cost less than or equal to C of P. But since we assume that the path P is an optimal shortest path, this means that the cost actually has to be strictly equal to 0. Sorry, strictly equal to cost of path. So in particular, you can just say you get a path whose cost is same as the original path which had a cycle in it. Okay. All right, talk to your friends for half a minute. Let me know if any questions. If not, we'll move on next to try to design a dynamic programming algorithm for this. All right, are there any questions? Alex.
Sorry, for the homework that we had before, I recall we had a directed acyclic graph. Did that have negative weights in it?
So the question, I believe this was 8.3 or something. Right, so the question on the DAG, you could have negative weights.
So then once we reduce the problem, we've already solved it.
No, because this can have cycles. The DAG didn't have any cycles in it.
So we're going to remove the cycles, right?
No. Oh, so this is not the actual algorithm. This is just the argument for saying why there always exists a shortest path that doesn't have any cycles in it. I have not solved the actual problem. All I've argued is the proposition that if there exists a negative cycle, if the graph has no negative cycle, then for all pairs of vertices there exists a simple path between them.
I thought this meant we were going to figure out how to remove the cycles and then.
No, this is just for the proof of this proposition. The problem with trying to remove cycles is there can be exponentially many cycles in your graph, and so then just at that point you're dead. Yeah. Well, you're not dead, your algorithm is dead. So, yeah.
If G does have a negative cycle, does that mean there technically is no first path to cycle?
Right, so the problem with the graph having a negative cost cycle is there is no finite path that will have the shortest cost, because you're right, you can just keep on going over and over again and get minus infinity. Yeah. So it turns out we're not going to cover that in class, but there's an algorithm in the book which actually allows you to check whether your graph has a negative cycle or not. So it's not something, so if you were to run this algorithm in the wild, you can check whether it has no negative cycles. If that's the case, then you run the algorithm that we're going to see. Any other questions? All right, let's move on. And as we've been doing for all of these dynamic programming algorithms, we're going to change tax a bit and say, instead of giving me the actual shortest path or the actual path, just give me the cost. So that's what we're going to do. So assume only interested interested in cost of shortest paths. And so we'll just solve this problem using dynamic programming, and as we've seen for the other two problems, once you have the dynamic programming and you solve all of these sub-problems, you can recover the actual shortest path from all those values. Okay. All right, so let's go ahead and try. So what I'm going to do is try to come up with a dynamic program first that looks pretty much like the dynamic programming that we saw for the weighted interval scheduling problem, see why that won't work. Then we'll go to come up with a dynamic programming that kind of looks like what we did for the subset sum problem, and then see why that has issues. And then finally we'll see what is the new insight that we need to put in to kind of get a dynamic programming algorithm for this case. Evan. Sorry? Oh, thank you. Yes, indeed. All right. So the idea is kind of use weighted interval scheduling like. So this is not a well-defined term. Dynamic program. So in particular, what we're going to do is, let's say opt of S is cost of shortest ST path. Okay. So like we had for the weighted interval scheduling problem, we had opt1 to opt_n, which is going to just define the optimal cost from S to T. And one of the observations that we'll also use at the end is to note that if you want to go from S to T, unless S is equal to T, you probably need to take one edge out of S, right? Unless there exists no path. So you look at the case where S has a bunch of neighbors. And let's say we know that the shortest path from S to T actually takes the first edge is S to U. Right? Now, if I know the shortest path from S to takes the edge from S to U, what path should I take from U to T? The shortest path, right? I mean, there's no reason for it to do anything else, right? Okay, good. So if shortest ST path takes edge S to U, then we do know that the cost of the shortest ST path is same as the cost of the path from S to U, sorry, cost of the edge from S to U. And then we just take the shortest path from U to T. And in particular, in general, we don't know which edge the shortest path would take. We cannot, for example, take the shortest cost edge out of S. We've already seen that doesn't work. So the best way to combine all of this is, since, well, I don't know which path it's going to take out, so let's just take the minimum of all possible ways of getting out of S. Okay. So in general, you can define opt of S to be the minimum over all U such that there is an edge from S to U of the cost of the edge from S to U plus opt of U. Okay. All right. Okay. So it turns out that this recurrence is actually true. So there is nothing wrong with what I've written. It's a perfectly mathematically correct statement, right? But the issue is just having a recurrence relation is not enough, right? So remember, we needed to satisfy three things: polynomial many subproblems, you need a recurrence relation, and you need an ordering, right? So let's go through one of them, and one of them will fail, right? So we're going to look at number of subproblems. So in this case, how many subproblems do we have? Mehmet? Sorry? No, so, okay. So you have one opt of S for each S, right? So you need one subproblem for each vertex. And so since there are n vertices, I'll have n subproblems. Okay? So I should have clarified this. You want this for all S. Okay? So the number of subproblems is just n, which is a nice polynomial thing, which is good. The second thing we wanted recurrence formula, and that we already have. So the one thing that needs to fail and will fail is the ordering issue. Okay? So we need a good ordering. By any chance, do you guys see what the issue might be? Mark.
The solution for you go back through S.
Right. So the problem is if you have an edge from S to U and an edge back from U to S, you'll have a cyclic relationship in your recurrence relation. Right? So let's make this precise. So let's say here's one simple graph on 3 vertices. So an edge from S to U of cos 2, U to S of cos minus 1, and let's say you just have an edge from U to T of cos 3. So in this case, opt of S is 2 plus opt of U. This is correct, this is fine. If you look at opt of U, it's minimum of 2 choices. It's either you go from 3 plus opt of T, or you take minus 1 plus opt of S. But the issue is now opt of S depends on opt of U, and then opt of U depends on opt of S. So there is a dependence, cyclic dependence between 2 subproblems. And once you have a cyclic dependence between your subproblem, there's no way you're going to be able to order all of them so that one subproblem in the middle only depends on the previous subproblems. Okay. So I said there's a problem. Opt of S depends on opt of U, and opt of U depends on opt of S. Okay. And so this implies there is no hope of total ordering. Okay. That makes sense? Right? Because I mean, in the order, either S has to come before U or U has to come before S, and in at least one of those cases, if you go in order, the actual value won't be ready for you. Okay? And again, so what this is saying is you can come up, and this is where dynamic programming starts to get tricky, right? So you can come up with recurrence relations or recurrence formulas, but it need not always work because you need to satisfy all the 3 properties. So in this case, we came up with one that had polynomially many subproblems. There was a nice recurrence formula, but we couldn't get a good ordering. All right. So then you could say, well, maybe this is happening precisely because of the same reason that the original failed attempt for subset sum didn't work, right? Because what we were doing in the subset sum originally was only looking at the numbers W1 to Wn and ignoring the budget part. Right? So here you could say, well, we are ignoring the graph to begin with. So maybe let's put the graph in as another parameter, and maybe that will work. So in our 4th attempt, so like subset sum, let us use all parameters. And so for example, one option could be you could define opt S of G, and now we are explicitly adding the graph as being another parameter. Okay. So it's cost of shortest ST path in G. And the basic intuition for doing something like this is, well, if you take the edge from S to U, right, let's just, at the very least, let's just delete this edge anymore. Right? Because if I already I'm taking this edge from S to U, why should I take this path again? Right? And then the hope is, since I've dropped one edge, my problem becomes shorter, right? So I have U and I have another graph which now has one fewer edge than what you started off with. Okay. All right, so again, if you had an edge from S to U, you could say opt of S comma G is cost of SU plus opt of U comma G, where you actually drop this edge SU. Okay. So I have another subproblem, and I'm now making progress, right? So I've dropped, I've made the graph a bit smaller. Okay. Or more generally, since S might have more than one outgoing edges, I'll have opt of SG is minimum over all possible neighbors of S of cost of SU plus this quantity over here. Okay. So you look at all possible things that are going on. So this actually turns out will solve this cyclic issue with the ordering, right? Because when you go from, in this case, you go from SG to U comma G minus this edge SU, and this opt of U is something different. Right? So there is no, you don't get the same opt twice. You get the same S, so U might depend on S. Sorry, S might depend on U and U might depend on S, but the actual G values would be different. Okay. So this solves the ordering problem. But there's still an issue, and if you see, well, you know what's going to fail, because I've already given you a recurrence relation. I've told you that the ordering won't work. So the number of polynomial subproblems is something that should fail. Do you guys see why you won't have polynomially many subproblems? Grant.
Keep changing the graph.
Right, so the issue is we are dropping one edge, right? But in general, you might not drop one edge. You could keep on dropping multiple edges. And in particular, your dynamic programming should be able to handle all possible ways of dropping edges. So that's exponentially many subgraphs. And that's a problem. Right? So, okay. So the thing is, so if you kind of try to unroll this recurrence, we need to compute opt of S, and the graph would be all, again, the set of vertices don't change, but I need to look at essentially all possible subset of it. Now you might be able to kind of, tweak certain things and save off certain of these subgraphs, but ultimately you still have to look at exponentially many of these. Okay? So these implies exponentially many subproblems. Okay. Okay, so I have a minute. I'll at least give you a quick overview of what we're going to do next, and then we're going to fill in the details next time. Okay. All right, so here's our final attempt. And the main observation here is what we really needed to foil kind of this example was not we didn't need the full power of the entire graph, right? All we needed to make, so for example, the following observation is enough to kind of foil this total ordering, which is, say, if I knew that the shortest path from S to T had 10 edges, then when I go to U, I only need to look at shortest path that uses 9 edges. Right? So and this is kind of the main insight in most of dynamic programming algorithms, is sometimes you have to introduce a parameter that's not directly given in the problem statement. So you have to kind of extract the parameter that's relevant and then solve it. So the idea is, think of a measure of how close we are to the final destination T. And in particular, what we're going to use, and this is going to be a final set of subproblems, we're going to have opt of S comma I, which is cost of shortest ST path with at most I edges. Okay. And you can think about it and convince yourself that this is enough to kind of not run into the problems that we are seeing over here. And indeed, this will work. So on Friday, we're going to go through the process and make sure all things work. Sorry for going over time.